Hi, welcome to Lecture 5 of Week 2 for GEOEL221 on mapping and map making basics. Let's take a step back and have a look at what field geology is really all about. It's a systematic investigation of part of the Earth's crust involving 5 steps. First is preparation. Second is location, description, and measurement of geological features, and data collection and taking rock samples. The third is classification and synthesis, i.e. data reduction and analysis. Number 4, interpretation of the data, making geological inferences and geological engineering inferences. And lastly, presentation of the results in maps, cross-sections, and final reports. Part of this can be an iterative process where if you complete certain stages and you need to go back for more data collection, it's quite possible to do so, to at the end of the day come up with the best presentation of the results that you can. So in this lecture, we're going to start talking about the last step, the presentation of results, specifically looking at maps. Here's an example of our goal to make a map. This is Southern Ontario, and we can see Kingston highlighted in the yellow K. The blue to greeny to purpley colors are part of the Ordovician and Younger sedimentary units, and you can see the Precambrian units in the Frontenac Arch and the rest of the Grenville province toward northern Ontario. Here's an example from Colorado in the United States of a landscape where we can visit the outcrops to make our observations and interpretations and identifications of what the rocks and structures are. And then on the bottom, what these rocks look like on a map. And in this case, this is a 3D model of a map that's overlain on the topography of the area, which is pretty neat. We'll talk more about topography next week. You can see in this case we have very general names of rocks that are written. We have, broadly speaking, Precambrian, igneous, and metamorphic rocks on the left. And this is what's called a map unit. There may be rock types within that are too specific or on too small of a scale to depict in the context of the map scale itself. Here's this map as is shown on paper normally. We can see the different map units correspond to different colors, and the summary of the legend, just showing the correlation of the map units, is shown on the left column, where the oldest units are on the bottom and the youngest units are at the top. There are also other features of the map, including a north arrow, scale and scale bar, and a legend of symbols, including symbols for contacts, faults, synclines, strike and dip of bedding, as well as the strike and dip of foliations. Here is the full legend, or a piece of the full legend for this map, and on this you can see each map unit contains a more specific paragraph format description of the rocks that are included within that unit. I encourage you to take some time and read through some of these examples to get a sense of what information is contained within a map legend. A few notes about legends in general. Legends use colors, and there are conventions. For example, blues are typically associated with carbonates, and pinks are typically associated with plutons. We'll generally tell you what colors to use so your maps are consistent and readable. Rocks are normally put in age order that I've been mentioning throughout the course, where the youngest rocks are at the top of the legend and the oldest rocks are at the bottom of the legend. Sometimes other events are shown explicitly in the time order, such as in this example, we can see there are some unconformities noted between some units. The letter codes on published maps from geological surveys, such as this example, are usually capital letter age, lowercase rock type, but sometimes numbers are used as well. Map units depend on the scale of the map. And as I mentioned, a map unit does not have to be a single rock type. Here's an example from much closer to home, north of Kingston, and the legend excerpt for clastic, silicious, gneisses, and schists is shown here, where you can see that there are actually 4 rock types contained within this one unit. The legend contains the geological history in summary, basically, or another way of putting that, the legend shows the conclusions and details of the map units. In this example, here's a full legend again, showing oldest to youngest from bottom to top. This is a bit of a shorthand example, but the map legends that you create should include a full description of each unit, not just the names of the rock types. So how does our map start? We collect geological data in certain locations, and it's very easy to record data on air photo bases, or we can use base maps. You're probably familiar with Google Earth satellite imagery. Google Earth is imagery, but it's not an air photo. When you get to an air photo, there's a much higher resolution and clarity that you can find, and you can see features down to the cow scale, but typically not the penguin scale. An air photo is shown on the right of this slide, and north is normally up along the edge of the photo frame itself, and there's always a unique number in the corner for a registration number. Using air photos and satellite images are very useful for both navigation and traverse planning because rocks tend to show up on them quite well. Rocks are more reflective than vegetation, and you can see a few examples of what look to be rock outcrops that I've highlighted on this image. And so by looking at this image and identifying ahead of time where the rocks are located, we can use that information to plan our traverse, i.e. where we're going to walk around in the field to go find the rocks in the area, to look at them and make our observations about the geology. Here's a very brief primer on air photos. You're going to learn a lot more about this in GEOEL221 and terrain evaluation. Air photos are collected from fixed-wing planes that fly predetermined flight paths, such as the example shown on the map, where in predetermined distances between images, they are able to collect photographs of areas such that a whole collection of air photos from parallel flight paths will have at least 60% forward overlap within a single flight path, and there will be lateral overlap between parallel flight paths between 20 to 40%. With that detail of overlap, we will always make sure that we won't leave any details out, and we can also use these to view them stereoscopically where they appear to be in 3D. By the way, we have an awesome air photo collection here at Queen's in the Stauffer Library basement. There's a link to the library webpage if you're interested in having a look. They may even have some air photos of your hometown. When we work with air photos in the field, we don't draw right on them. We put tracing paper or mylar overlay, and we tape this overlay paper to the air photo at the top. Once we've done that, we add the photo number to the mylar. We add some registration marks along the edges. You can see there's a notch in the edge of the photo frame that we indicate with the chevron. To make sure, in case the tape fails, we can realign our overlay mylar on the air photo at a later time. We also add a north arrow to our mylar and a scale bar. And one important note is we never trace in the road. Typically, it'll get way too crowded because many outcrops we see are along the road. We only put the tape at the top edge of the mylar because quite commonly it's useful to flip up the mylar to have a closer look at the air photo. That's not blurred out by looking through the mylar itself. If we don't have access to air photos, we can also make a traverse map directly on base maps. And base maps are also known as field slips in the UK and some parts of Europe. Base maps, like the one shown here, usually contain a north arrow, a scale bar, topography, contours, roads and trails, some buildings, some fence lines, sometimes gas pipelines, surface water bodies, and a latitude, longitude, or a UTM coordinate grid. Here's an example of a traverse map. A traverse map is a graphical record of what you saw and measured, and this map complements your field observations that would be recorded in more detail in your field notebooks. Traverse elements to include on a traverse map are scale, structural symbols that you use, both in a very brief legend as well as when you use them in place, contacts between rock units, units colored in with proper colors, pace and compass info if needed. So a pace and compass info tell you graphically exactly what direction and distance you walked in order to complete the traverse. And lastly, title and authors and the date. So what are some geological symbols that we include? Here are two examples from the same map from Colorado. You can have the strike and dip of a fault, and you can have strike and dip of bedding, among all of the other types of structures that we've been talking about so far. Map symbols are conveniently located in the back of your field notebooks. These include strike and dip measurements for planar features, such as foliation, or icicle airing is a common application of this symbol, cleavage, joints, bedding, and faults. For trend and plunge or measurements for linear features, these include lineations and nested lineations as well. Other features include contacts between rock units and folds. Here are the pages where you can see the symbols for the contacts, lineations, folds, and faults in a bit more detail. And again, these are all in the back of your field notebooks. When you're in the field and mapping, the strike and dip values are written in your field notebook, like I talked about in the last lecture. Remember that the strike is always written as 3 digits, followed by a forward slash, and then the dip, which is written as 2 digits. Once you've written down the numbers in your field notebook, you then plot them on your traverse map right away, and you would plot it on your field map when you get back to the office later. Here are the steps in drafting map symbols and outcrops on your map. Step 1 is plot the exact location where you have made the measurement as a small dot on your traverse map. The station numbers shown beside the dots, the S- number, are reference numbers to refer back to the station numbers in your notebooks. These are plotted only on your traverse maps, and they are not transferred to your final map. Strike and dip values are plotted on your map using the correct symbol and in the correct orientation. So if you remember, a strike value is the orientation or azimuth within the horizontal plane with respect to north. Here's your Douglas protractor illustrating this concept. North has a strike value of 0, 0, 0. The numbers increase as we work toward east, which is 90 degrees, or written as 090, down to south, 180, west 270 degrees, and we get back toward 359 degrees, and then 360 degrees actually becomes 0, 0, 0 again, because we're back to north. So the strike line is plotted on your map with a ruler, moving clockwise from true north in the exact strike orientation that your measurement was taken in. In this example, at station 19, the strike value is plotted as approximately 235 degrees, and the dip value is 50 degrees. Dip is, by definition, perpendicular to the strike orientation. So the short dip tick is drawn perpendicular to the strike line, and the value of the dip, 50 degrees, is written on the measurement itself. A style comment is it's important to draw strike lines that are 12 millimeters long to make sure they're visible and distinguishable from other features on your map. Step number 3, we dot in the outline of the outcrop that we have observed the shape and location of, and we color in the outcrop lightly using the colors in the legend for the map units that correspond to each color. Step 5, once we've plotted multiple outcrops, and in this example we have station 19 as an orange colored map unit, station 20 is a brown colored map unit. So there is a contact between these two outcrops somewhere. To indicate this on our map, we draw in a contact line. In this case is a dashed line that separates the different map units. And now at this point, we're starting to transition a little bit from raw data into interpretation. Because we don't know the exact location of the contact in between these outcrops, that is a bit of an interpretation. However, it is constrained by observation between these two outcrops. So in this case, the accuracy of the contact is fairly high. Step number 6 is to shade very lightly the area inferred to be underlain by the same map unit. So the space on the map outside of each outcrop observation, but within the dashed line area of the contact, you would shade that in the same map unit color as is in the outcrops, but it's a much lighter coloring than the colors inside the outcrops themselves. A very important point, traverse maps are plotted and colored in the field, not on the way home, such as on the bus, in the vans, or even later than that once you get home. You can think of yourselves as a bit of a PI or CSI Miami investigator, where you always see their notebooks out and them writing down their observations in the field to make sure that they get the detail correct by writing it down in the moment that it's collected. Once we have our traverse map and we're back in the office, the next step is to use our traverse map and field notebooks to make a final map. Here's a nice example of what a final map would look like, and you should strive to make excellent looking maps like this one shown here. Zooming in a bit, your maps should look like quite a lot like this, except for the numbers beside each outcrop is an older style of map convention. Generally, map units are not numbered in this way. But you can see here the darker shading within the outcrops in each color versus the much lighter shading in the area outside of the outcrops that is inferred or interpreted to also be of that unit for the rocks that are underneath the vegetation that we cannot see. Neatness is very important for both field or traverse maps and office maps. Here you can see a traverse map on the left on Mylar that's overlaying an air photo, and compared to the final map on the right. The neatness of these maps is helped a lot by the use of your micron pens, using either the 0.2 or 0.25 millimeter together with the 0.5 millimeter micron pens. And you would use the different thicknesses of pens for different map symbols that will be identified for you in a style guide that we'll talk a bit about later. So the elements of a final map are a title, a neat line or a box outlining the whole map, a north arrow, a legend, and a scale that can be either numeric or graphic. Sometimes there's also an inset map with a reference grid, an overall balance of the size of elements compared to the map itself. You can have supplemental information on the map outside of the bounding box, and projection or coordinates information, such as if you're using lat-long versus UTM coordinates. Broadly speaking, cartography is about making effective maps that communicate clearly in the context of who our viewer is, what they are trying to accomplish, etc. Whenever communicating, always make sure you start with imagining who your intended audience is. So you make sure you include the correct information at the appropriate balance of detail. As you can imagine, or are probably starting to appreciate, maps can get very complex. You'll start with drafting and making maps in this class and in GEOEL300 and a few other upper year field courses, but there are also courses in cartography, in geography, and intro to terrain and GIS courses in upper year GEOL and GEOE. So if you're interested in that aspect of map making, have a look out for these as you go through your program. Geological mapping and scale. I've talked a bit about this, but this slide I've made to really try to drive this point home. Maps can be made on different scales, and different scales of maps capture different amounts of detail. So scales are typically presented as a ratio, such as the example on the top right, the scale showing 1 to 24,000. What that means is it is a ratio of the distance on paper of that map to the distance that it represents in the real world. So a scale of 1 to 100,000 on a map means that 1 centimeter on the map is equivalent to 1 kilometer in the real world. So one of the questions that we have to ask ourselves as we're making maps and going on traverses is, what level of detail can we actually incorporate into our maps? And for that, to figure that out, we simply need to look at the tools we're working with. So if you take your 2 millimeter drafting pencil, even with a sharp point, the smallest dot you can really get, as shown on the bottom left, is about 0.5 millimeter in real life. I've used my handy field scale card to show what that looks like at different map scales. So in the middle, if that dot were plotted on a map that's a 1 to 50,000 scale, that dot represents about 20 meters diameter. And if we go further to a scale of 1 to 250,000, that little dot represents about 100 meters at that scale. So keep all of that in mind as we go through this course, and especially when we're getting into the field and you're mapping rocks. Make sure you keep in mind the scale that you're mapping at so you can adjust the level of detail you're trying to map accordingly. To wrap up this talk, here are a few different examples of maps, and I encourage you to have a look at these on the slides to familiarize yourself with how maps look in general, their elements that they include, and the different symbols and labels that are generally found on them. I should say you're also going to find, as you go through your studies and into your career, there are many different conventions on map symbols, which is why it's very important to always include a legend on your map, because one symbol that could mean gneissic layering to you may mean a joint, or it may mean bedding, or it may mean a fault to somebody else. Again, note how the outcrops are colored in darker shades, and the covered ground, i.e. where we've interpreted the same map units to extend in between outcrops, that area is colored in lighter shades on the map. Here's another example of that. You'll notice here that the shapes of the outcrops are getting a bit funky, and when you're in the field mapping, part of what you do is identifying the rocks and describing them and making observations of the structures and all that. But the first step of knowing where you are is also equally important. You need to know exactly where you are, so when you're recording the outcrop on your map, it's in the right place. It seems simple, but it's important to take the time to actually do that. And when you're on the outcrop, walk all over the outcrop to be able to map out the irregular shapes and orientations that the outcrops are actually in. To summarize, geological map elements include title and authors, scale, north arrow, legend with full descriptions of the rock units, structural symbols, the units colored in where observed and dotted in outlines of outcrops, and major landmarks and topography if not already included on your base map. I will put a style guide for maps in this course on OnQ, which will help make your maps look awesome. Thanks very much for watching. Please add your comments and questions to the lecture Q&A Google Doc that's posted on OnQ, and have a great weekend. Bye.